Well, hello everyone, and welcome back to Adrian's Digital Basement 2. It's Super Mini Mail Call, so let's get right to it. First one here comes from Gordon in Shawano, Wisconsin. Hi to all my Wisconsin viewers. Looks like we have something with a note. Let's check out the note. All right, so this comes from Gordon at Great White Retro. As I mentioned before, good day. Thank you for taking a look at this ATI Graphics Solution 3. As I explained in the email, the text mode on this card is showing garbled characters, as if bit 2 of 0 to 7 was stuck low. The card otherwise seems to work with CGA and Plantronics graphics, though I also struggled getting it to work with monochrome monitors this card claims to support. Yeah, I think this is an EGA type card, and that definitely supports monochrome, but if it's only CGA and Plantronics, then maybe not. I've already swapped all the RAM and 2 of the related bus ICs and replaced some busted traces, but I have gotten the same results. I've included the original RAM and 2 spare bus ICs with the card. Please keep the card and spare parts and help me understand what I missed. I already have another card to use until I can find a replacement Plantronics compatible card. I'm hoping to make my IBM 5150 a display piece for upcoming shows this year. Thanks again and good day. So this is a Plantronics compatible card. Let's see what this card looks like. I'm not super familiar with all the various ATI cards, like by name at least. I wonder why this is kind of wet looking. Is that maybe Deoxit? I would say this is a normal EGA card, but I don't think so because it's got a 6845 on it. And typically, well, when you got a 6845, this is more CGA style. So we have extra RAM chips that Gordon mentioned. These are 416, so 2 of these is 16 kilobytes, 4 of them 32K. How many do we have? It looks like we have 64 kilobytes of them. And as far as the bus transceivers go, or whatever these are, 257s, off the top of my head, I don't remember what those are. Now looking at this, that's definitely the correct type of RAM. And Gordon said in the picture in the letter, it looked like it was working. And these are obviously the 2 ICs that he swapped out, 257s. So I guess I need to get a motherboard and we will give this thing a test. Graphics Solution Rev 3. Also curious, looks like it has a 25-pin header spot for a parallel port. Interesting is I don't see any additional ICs that are missing. So I kind of wonder, oh, okay, well they just go right to this header. So it is my assumption there was an add-on board that plugged into this, something that kind of sandwiched on top, and perhaps it connected to the board there as well. So this picked up the ISA bus, that connector, and then parallel port, and then you had a different slot connector with your parallel port. So the circuitry for the parallel port is not on this card. So taking a look at this, yeah, we definitely have, well, a working card, but definitely seems like there's something going on with the access of the card to the RAM. What we'll have to do is get this thing up and running, and then we can run some further tests to figure out if the problem is on the bus side, that's an ISA bus talking to the card, which is very unlikely, or if there's a problem with this big chip talking to the RAM, which is more likely the problem, and unfortunately, obviously not fixable with this custom chip. Now, Gordon mentioned that this card does offer Plantronics compatibility. And I mentioned in the email that another card that does that is this VTech CGA/MDA card. And the funny thing about this card, I made a video in the past, and I'll try to link to that video in the description, is that there are unpopulated jumpers when you first get these cards. And these were bundled with many, many VTech clone computers. Well, when you install these jumpers and then you set them up exactly as you see here, let's zoom in a little bit. So 2 at the top, 1 at the bottom. This one's on the right. That one's not populated. It puts this card into Plantronics compatibility mode. So it's still MDA, it's still CGA, but it's also Plantronics. And that's pretty cool because Plantronics cards or compatible cards aren't super common. I have a little bodge or 2 on the back here. Pretty sure I didn't do that one, but this one I did do. I think it was when I installed this jumper. It looked like, I didn't know any of them did, and it looked like there weren't traces for this one or something like that. I forgot what it was. I think I had to go from the middle pin, which is kind of hooked up to these resistors normally on all of these jumpers, on all 3, and I just had to jumper it because the trace was missing for that particular jumper. I don't remember which one of these does Plantronics compatibility, but like I said, if you have one of these cards or you get one of these cards, set the jumpers up like this, and you will have Plantronics compatibility as well. This also has 64 kilobytes of memory on board, which is required for Plantronics, but also Hercules compatibility, which this card has as well. All right, well, let's grab a motherboard. I just happen to have this Pentium motherboard handy, so we're gonna use this for testing. I need to find my right angle adapter. Here it is right here. This will allow us to plug this card in. Let's see how this works. Okay, so that's the way the card would normally go in. So if I plug it into this adapter, then we can plug that into the motherboard, and that will allow us to probe this while the system is running. Now, this is a riser that came out of I don't know, some clone computer. You can buy modern recreations of these if you don't have access to get one of these clone ones. I don't know how much these cost, if you can even find them online. I found this at eWaste. But if you're doing any kind of troubleshooting on ISA cards, they're just very, very helpful. All right, I'm just gonna get this motherboard set up, plugged into the RGB to HDMI, and let's see what we can figure out. All right, I think everything is ready to go. I don't have a keyboard plugged in, but let's just see what this card does it all. I'm just gonna set this to, I'm gonna set it to CGA. I mean, I assume that's gonna be close enough, at least for initial testing. Here we go, 3, 2, 1. All right, obviously we have a good CGA image, but we have lots of issues here. Now, the funny thing is that certain characters look fine. Like we have 200, and it should be megahertz. That's above the RAM count. That's what this CPU is on this motherboard. I'm pretty sure that's what the CPU is. So the M isn't working, but the H, the Z, and the 200 are. Now, as Gordon alluded to in the letter, that actually gives us some clues as to what's going on. Like we have a stuck bit, right? We have a stuck bit that is probably stuck at either 1 or 0. So anytime a character, like the background space or the 2 or the 0, the bits that make up the character, the stuck bit doesn't affect, because if it stays stuck at 1, that particular bit in position as 1 may already be a 1, it's stuck as 1, so it doesn't really matter. But then when it goes to print the M, you get an I instead, because that bit is still stuck in the wrong position for that M character. So, okay, let's ask Gemini. Let's see if AI is useful for anything, because I'm skeptical. What is the binary bit pattern for the ASCII character M, capital M, 0, that's the number 0, and 2? Let's see if it can even answer this correctly. Okay, so it gave us answers. Hopefully it's not lying. Now, what we need to know is what the character or the bit pattern is for the character I, because the capital M became the capital I in megahertz. So what is the bit pattern for I? Right. Let's go one step further. Which binary bits are different between the ASCII characters M and I? We can tell right there that it's the third bit that is the one that is stuck, and it's obviously stuck at 0, and that's why the M becomes an I. But I love how what it's saying here is completely garbage. The 6th bit is divergent, right, between the first 5 most significant bits, 1 and a 0, which we already identified. Then the 7th bit is also different. M has a 0, I has a 0. Yeah, so different. The 8th bit is the same. Okay, anyhow, what we know for sure, we start on the right, that's the least significant bit. What we can tell by just looking at it, it is data bit 2, so 0, 1, 2. That is the stuck bit, and it is stuck, go away little thing, it is stuck at 0. All right, so what this doesn't tell us though is the problem the computer talking to the video card? Like anytime it tries to talk to the card and transfer 8 bits, because this is an 8-bit card, does it always just transfer a 0? That is basically impossible, because the card is initializing, and it wouldn't be able to initialize at all if this bit were always stuck on the bus side. So I don't know about these 2 transceivers or whatever these 2 chips are that were changed by Gordon, but if they interface to the ISA bus, then there was no real reason to change those, because it's just pretty obvious to us that the issue exists somewhere else in the video subsystem, and it's almost certainly not going to be the ISA interface to the video card itself. We can easily test that though. We just have to boot up into DOS, and we can use debug. All right, so I should be able to hit F1. Looks how funny it all looks. But the system is booting up without any issue. Now, one thing you can do really easily is just run checkit and try to do a RAM test, because checkit has a video RAM test function. Obviously, you can't really read the screen very well. I happen to know, where's video? I think this one is video. Yep, this is video, and I think this is the RAM test. So we'll just do this. This is going to test the character text modes. Right there, it's basically telling us that 16 kilobytes passed. Now, it can only test the first 16K of RAM. This card has more, has 64K, we've determined. But this test is designed for CGA cards, and that's why it only tests the first 16K. But it passed. It would tell us if there was a bit error storing and reading back memory. So this tells us that it's not the RAM and it's not the ISA bus. This is something to do with the interface between the RAM and the video display subsystem. As it displays text or graphics on screen, it's constantly reading back all the contents of memory, at least for the mode you're in. So when you're in text mode, it's only reading back a little piece of memory. It's reading it back over and over again, 60 times a second, as it refreshes the screen. And that's where the problem lies. Because what this test is doing is it's storing arbitrary data into RAM and then it reads it back. Because the ISA bus and the CPU is able to read and write from the memory. If what was stored in the RAM was getting lost, then it would read back wrong too and it would fail this test. And what this is doing here is it just tested like the various pages of RAM and those are fine as well. And you know, obviously we're having problems. Now, here's an interesting thought. What if the problem is the character generator? I don't know where the character generator is on this. I assume it's inside the main ROM, EPROM here. And we'll be able to tell if that's the case by just looking at the graphics modes. So check it, will be able to tell us, we'll be able to see a graphics mode in a second. There's a graphics mode. The dotted lines in the grid should be straight and uniform. Everything looks fine there. Let's make it bigger. See where it says, is the screen displayed correctly? There's a line that only goes halfway across. That's not right. Let's try the different modes. It should look like that. The line should go all the way across. So that's odd. But one thing we can see here is that the graphics modes are working. That kind of implies that this, again, isn't a RAM problem, that this is like a character generation problem. And normally with, well, like a CGA card, there's character generator ROM. And as the contents of memory is being read out, and it's here in text mode, when you have a value of like, say, 73 in RAM, then the data bus that's coming out of the RAM chips is connected to a character generator ROM on the address lines. And what that does is it selects the correct character and the output of the character ROM is then serialized and then displayed on screen. So if like one of those address lines inputs to the character generator is stuck, then the characters are going to look wrong, but all the graphics modes are going to work. Again, this is weird that that line isn't going all the way across. That could be a weird side effect of this card though. It might not be a fault. This again are the character problems. What we need to do is run a game. Let's run a game. Okay, we're gonna use Planet X3 CGA mode. First we'll just do normal CGA graphics. All right, yeah, there we go. So it looks perfect, right? We have 0 issues with this graphics mode. I don't remember how much memory this graphics mode uses, but I think it's using 16K. So it's using 1/4 of the memory on this card. Let's try running Plantronics mode if this card does support it. Let's see what that does. I think it's 1, 2, 3, 4, 5, 6. I think it's 6. It says 2, but it's 6. And we'll do no sound for, whoops, that was the wrong option. Okay, anyways, there's Plantronics mode, and it's freaking working too. Now, Plantronics mode is actually 320 by 200 resolution. This is using graphics assets from the Tandy lower res mode, like 160 by 200, I think, which is why it looks kind of blocky, although the text is high resolution. But as you can see, perfect, absolutely freaking perfect. I mean, this is pretty much telling us that it's definitely not a RAM problem. It's definitely not a problem with the ISA bus. This is entirely a character generation problem. Now that begs the question though, where is the character generator on this? It's gotta be this chip right here. It has to be. And now that I think about it, this is a CGA card. This card doesn't even need a ROM. So EGA, VGA cards, they use a ROM chip because they have different registers than CGA. And what happens is when the system boots, it actually executes code from the ROM chip on an EGA or VGA card or any other type of card that's better than CGA. And it initializes the card based on the code in the ROM. The thing about CGA cards and monochrome cards is the system BIOS, even on this Pentium motherboard, initialized the video card. A CGA card, for instance, has to be 100% compatible with an IBM CGA card. I mean, it can have extra features like this one does, but ideally the base functionality is identical to a real CGA card, and that's why it uses 6845, because the BIOS is setting it up. So this chip right here is going to be only used for the character generator. Now looking at this chip, it's a 2764. That means there's 8 kilobytes of RAM, which is a good amount for a character generator. You don't really need that much for a character generator. Let's pop this chip out though. Sorry, it's like at the edge of the camera there. Let's pop it out and we'll take a look at it. First of all, I gotta turn off the computer. So it could have a bent pin underneath it for all we know. Came out very easily. I can tell that Gordon's probably had this out of the board. So got no bent pins, nothing looks out of the ordinary. Oh, I got some bodge wire. Didn't even look at the back yet. Looks like Gordon had to bodge things on a little bit. Putting the new RAM chips in, or the sockets in. Obviously the card's working though, so that didn't cause any real functional issues. But yeah, I'm gonna wager it's this. Let's put the card back in and let's see if it boots and works without this ROM chip in there. I'm assuming it's gonna work just fine. We're not gonna see anything. Well, we'll see a screen full of just white or some kind of garbage because the character generator, which I assume that's all that is missing, but we should be able to boot up and even run a game, for instance. I don't know if I'll be able to do that blind, but I could try. Okay, yep, there we go. So character generator, that's all this is. So the system should boot. So the reason why you're seeing these boxes that are lighter is because the RAM is working and the attribute data is stored in RAM, and that basically makes it bright or not bright, and also color and stuff like that, and there's no color on the BIOS screen. I hit F1. I don't know, I guess we had an error. Couldn't read it. I think the thing should be booting, maybe. I really don't know. Let's try running edit. Okay, yeah, so we're in edit. So we have no characters, but we obviously have attribute data working. So let's exit out of this. Oh, great. Alt F, X, don't save. Okay, I think that worked. All right, let's see if we can run Planet X3 underscore CGA 1 for, nah. Oh, it works, yes, okay. And obviously graphics modes don't rely on the character generator at all, right? They're using the RAM for bit planes and stuff like that, and the Plantronics mode would have worked. I just forgot what number it was. I think it was 6, maybe 5, I don't know. Anyways, I knew CGA was 1 and it works fine. Now the character set you might see in a graphics mode, that comes entirely from the ROM BIOS. That doesn't come from the chip that I've taken off this board. So I think what this is telling us that here is our issue is either this ROM chip is bad, or the connectivity that goes from the RAM through these buffers and stuff like that, those could be the problem. So I think what we need to do is put this on the EPROM programmer and read it out, because we need to be able to see that data that's in the chip, make sure that it's not repeating, because if it is, then we're not going to see like the bit pattern for the capital M. We're just going to see capital I twice, and all the other letters kind of duplicated. Okay, I have the chip in the programmer. I'm going to turn off check ID. We're just going to read. All right, now it's hard to make any sense of what we're looking at, so I'm just going to save this, and we're going to open it up in a proper hex editor. Now, it's not super easy to look at a character generator ROM like this and know that there's a problem. I'm just sort of looking for repeating patterns. Now, it's quite possible that this thing only needs a much smaller EPROM. They just use this larger size. So there may already be repeating patterns, because it might only be, for instance, 4K in size. And let's look at these parentheses there. That's a good, easy pattern to recognize if we see it repeat. And I don't see any repeating at all, and at least for that. Now, I happen to have this font editor program for the Commodore 64, this one, and it generally works, or it should show us something if we open up this ROM chip. Let's see what we see when we open this. Yeah, look at that. It totally does work. I freaking love it. I freaking love it. It looks like what we're looking at here is that first character set, which is a single pixel wide, and CGA does support 2 different character sets. Just normally on the CGA card, well, you have to like jump or something to change it, and I made a video about that a while back. Maybe this card is selectable. There's an extra register or something to do that. So maybe there are 4 fonts, and this program doesn't support any of the larger files, so it's not showing us the rest of the characters, right? We're only seeing those first 256, even though I think this ROM is going to have 4 character sets. Now what this tells us, because we see all the letters there's nothing repeating, we can see the M, we can see the I, everything's perfect, this chip is good. There's probably nothing wrong with this chip. I mean, it's possible there's like it's like marginal, and the bus transceivers on the card are marginal, but I'm pretty sure what's going on here is that whatever takes the data out of the RAM and sends it to the address lines on this character generator, so it generates the right character, that is the problem. Now let's talk about how you address each character in the ROM chip. Remember, there are 256 characters. Well, this one has probably times 4, but let's just imagine it's only a 2K ROM, so it's got 256 characters. Well, each character has 8 pixels across, but it also has 8 rows of pixels. So when the circuitry needs to address one specific character, but then it needs to read out all 8 lines, there needs to be 8 bits of address lines for the 256 characters, plus an extra 3 address lines that are used to select which row of pixels you're going to be displaying, because it needs to kind of count through all 8 rows of pixels as it's drawing out the characters to screen. And that means you need a total of, I think, 11 address lines. I might be off of my math a little bit. So using the calculator, if we think about the fact that there are 255 characters, 0 to 255, each one has 8 rows of pixels, we times 8, then what you get is this, and let's switch to bitwise mode. And ultimately, those 3 bits at the bottom here almost certainly have to do with the line or the row of pixels that's being displayed. And when we turn this on, that gives us 2047 bytes or 2048 for 2K EPROM. And remember, this thing holds 8K, which is why I said it has 4 character sets in it. Now, I'm almost sure universally these character ROMs use these first 3 bytes, so the least significant bytes, to represent the line number. And then it would be the rest of these that have to do with which character is being selected. And then these top 2 bits right here are used for, if we turn these all on, these top 2 bits here are going to be used for the extra character sets. So as you select these on or off, you have up to 4 character sets available to you. Now we're talking about the characters that come from RAM and select which character in the ROM are used. It's these bits here that are currently set to 1. And we know that this bit right here, this is the data bit 2. Remember, I wrote that on the paper here. Data bit 2, that's the one that's stuck. This one is always going to be 0. So I have a feeling if we go look up the pinout for this EPROM and we look up address line 5, which correlates to data bit 2 from the RAM, here's that piece of paper again, we should see that as 0. But if we look at these other bits, or other address lines that are right next to it, we should see them toggling and doing stuff. And we don't even need to have the ROM chip in there for this particular test, because we know that the computer right now is probably trying to display text on screen, or at least if I exit the game. And that means that all of those address lines should be toggling. And the first 3 should be kind of flipping through as it's drawing the different lines of text. But yep, this particular address line 5 is going to be stuck. So let's use Gemini to ask it, what pin is address line A5 on a 2764? And I don't know if I can trust what it's going to say. Okay, there's a lot of junk here. No, none of this was helpful. You just need to tell me what pin on the chip it is. Oh, you're terrible. Show me a picture of the pinout. Let's see if it can do that. I mean, normally I just Google for it. Really? You can't show me a picture? It highlighted it. So why didn't you tell me that the first time around? So bad. Pin 5? I don't even know if I trust that. That's not trustworthy. Just show me a picture. What I normally do is just Google for 2764 pinout. Oh, it is actually 5, and it looks like it actually got them right. Pin 4 is A6, pin 6 is A4, which, yeah, that's correct. Okay, what I'm going to do is I'm just going to reboot the computer real quick. I just want to make sure that it's displaying a bunch of random text, not just like a little C prompt on DOS. All right, just on a random pin, just to see if we're getting a good signal, and we are 1 volt per division, so 4.2 volts. Well, 1, 2, 3, 4, 5. There's pin 5. Big old fat nothing on there. So I'm going to put the ROM chip back in just in case for some reason there's like, it needs to have loading or something. I don't know. Notches facing the right. Okay, there we go. We're back to exactly where we were before. So we see lots of activity there. That would be pin 3, address line something. Pin 4, Looks good. Pin 5, 0. Well, there's our problem manifested. So whatever is causing this to be 0, we know it's not the chip because it reads fine in the EPROM programmer. Whatever's generating that signal is causing this issue. And the next one down looks good as well. So this is the card reading out all the characters out of this EPROM. And basically our math told us exactly which chip was going to be bad on the EPROM. And there it is, bad. So I'm just going to power this machine off. And what we're going to need to do now is switch this into continuity mode. And what we need to do is just make sure that that pin, 1, 2, 3, 4, 5, is actually connected to something. There it is. That was quick. And there's no schematics for this board, right? So we have an LS273, pretty sure that's a latch or a flip-flop or something like that, which is very typical. And that's because it needs to hold that value as this counts through the other address lines to print out the 8 rows of pixels. So it's that pin. Let me mark that with something, and we're gonna need to go look at the data sheet for this chip, and we will need to figure out exactly the other side of this, because it's going to have an input and an output. Yeah, there it is. Oh, why don't we ask Gemini? What is pin 15 on a 74LS273? Let's see if this can do it. It's crucial to refer to the data sheet. It's a D-type flip-flop. Pin 15, based on the data sheet, it is the Q6 output. That means it outputs data stored in the flip-flop within the same IC. Okay, well, let's just go right to the data sheet. Well, that was a useless link. There's like nothing on here that tells us anything that we need to know. I mean, right. What we need to do is look at the input of that chip, just make sure that whatever's coming into it is also correct. Okay, so we know our problem child is pin 15. That's Q6. And it corresponds to 6D as the input, so pin 14. We need to look at pin 14 while the system is running, because you can take a look here that depending on the inputs, clear and clock, then the D is connected through to the Q. So when clear is high and the clock goes up, then D is high, then that makes the output high, or same thing, low and low. And then what happens is when the clock is held low, then what happens is the state of Q is just held from whatever it last was. And that's this right here, this QP or QO or whatever that's showing. Essentially what we need to look at is that D pin, which is pin 14, D6, that needs to be toggling as well. And if that's stuck at 0 as well, that means whatever's upstream is the problem. So just to reiterate, we're looking for 6Q, and that goes to 6D, which is pin 14. Now let's verify it's stuck. Yep, it is. So that's 15. And there's the input. Well, there's your problem right there. Either the output of this chip is shorted to ground internally or on the board. It could well be on the board. So we'll just switch back to continuity mode. Let me find the probes. And let's see if this is shorted to ground. It is not. It is not at all. The chip is bad. I mean, it's got to be. If we switch this into resistance mode, let's just take a look here. 5 megohms. I mean, nothing to indicate that there's a short at all. You know, 5 megohms or 15 megohms between it and other pins, totally normal. 14 megohms, yeah, 9 megohms. I bet you it's the same as like any other pin. So we'll go to 14, the input. Okay, 0.7, but that is hooked up to other stuff on the board. Remember, the output of this only goes to the ROM chip here. What's another output? I'm looking at the data sheet here. Pin 12. So this is pin 12. So that's pin 12. Let's see what it goes to. Yeah, 5 megohms. And pin 15, 5 megohms. So it looks the same. But we know the rest of the flip-flop outputs are doing stuff. We can turn this back on again. Now we'll switch back and we'll just take a quick look at the other outputs. So remember, that's the input going into the flip-flop for that particular data bit. That's the output that's stuck. There's another input. And there's another output. Now, this weird stuff, you see some activity, but you see those spiky parts. I think that's because the chip is not installed. It's going to be the same on all of them. But what we can see is there's activity in between this weird stuff here because the chip is not there. Input, output. So we know the flip-flop's being triggered properly. The clock and the data lines and all that stuff is working. It's just the output here is dead. Input, output. So we know for sure that that's the bad chip. So I'm just going to spend a moment to get that off the board, and that should fix this card. All right, the bad chip is out. I have a socket in place. I went in my parts and I found a 273, and it's from 1979, 45th week. So way older than this card is, but you know what? It should work. Look at that, just dropped right in. EPROM's back in. Notch is facing the correct direction. Let's give it a try. Okay, so let's do what I like to do, and let's not even plug the video in. Let's see if we see address line 5 now having activity. So turn this on. Start the fan. There's no spin on this motherboard. So pin 3, pin 4, pin 5. There it is. We have normal activity. And I think, what was it? 11, 12, 13, 14, 15. There's the output looking perfect. We should have perfect working video now. So we'll get this connected up. And there we go. Oh, that's why I was stopping. Floppy disk failure because it's in the BIOS. It's fixed. It's freaking fixed. What I want to see now is I'm going to run check it. And I want to see if the graphics mode has that line that doesn't go all the way across. Obviously, it's looking perfect now. So we go video, and I think it was in graphics mode. Yeah, okay. So the lines don't go all the way across. I guess there's just a slight weirdness with this card. Weird. I mean, I've tested that on a million other cards, and I remember those lines going all the way across. But I guess this card is not 100% compatible. Let's run Jim Leonard's CGA compatibility test here. And let's see what it's doing. Let's see how good this thing is. Okay, so it is definitely running at the right refresh rate for CGA. And this is working fine. That's how it should look, this test. And then row reprogramming, yep, that's looking good as well. Yeah, anyways, this thing appears to be fully compatible. This is it moving the picture around. It's completely normal. The flashing is just the RGB to HDMI. Let's exit out of that and start programming. This should have a scrolling screen. Yep, there we go. That's normal. It does that shifting. I think that's because this has more RAM than a CGA card. CGA card just has the 16K, but because this has the 64, it's doing that. And same with that one. Let's try Attack of the Pesky Robots, and this has a Plantronics mode as well, and I'm pretty sure that this has, yep, it's higher resolution. That's full Plantronics compatibility out of this ATI card. That's pretty sweet. That is pretty sweet. And of course it looks good, and because we're running on a Pentium, there's plenty of performance for the CPU, and yep, it's all good. The card appears to be working perfectly now. So, all right, so there we have it. We have a working ATI Solution 3, or Rev 3, or whatever this is, and the only problem with this card the entire time was this particular 273D type flip-flop. And using this $80 multimeter and oscilloscope, using some troubleshooting skills, a little bit of AI that really wasn't very helpful, we were able to get to the bottom of exactly what was wrong with this card pretty quickly, I gotta say. And I never know with these types of cards where there's highly integrated stuff with the big chip here, if we would have been able to fix this, but luckily we're able to determine that it was the character generator that was the problem after a little bit of testing. That chip worked fine in my EPROM programmer because that could have easily been the problem. It wasn't. So then we just went backwards from there and we found this chip and we could see right away that it wasn't working, and well, there you go. Those are the results. Proof is in the pudding. This card now freaking works. So Gordon, I hope that this video gives you some closure, and I hope that the troubleshooting steps I went through were helpful and maybe people watching learned something. That's always why I make these videos. It's fun to fix stuff like this, but it's also fun to teach other people the troubleshooting steps that I use and show the tools that I use to do the troubleshooting, to show that it's really not that hard to fix stuff yourself and to do it in a way that doesn't involve replacing a bunch of chips unnecessarily. And obviously Gordon went through a lot of struggle on the back of this board, as evidenced by the bodge wires here, that removing these chips were difficult. And that's why I like to get to the bottom of exactly what's wrong first before removing any chips from the board. Because imagine if Gordon hadn't noticed that these traces were bad, like if this thing was just doing a black screen or trying to fix it, well, changing these chips caused more damage to the board than was actually wrong the entire time, which was just this one bad chip. And that's why I really don't recommend, unless you really know what you're doing, removing chips from boards, because you can easily cause more damage, which can then make your troubleshooting way, way more difficult. Luckily, in this case, Gordon fixed all the damage that was caused by the removal of the RAM chip, so there was no issues there, and this card is now fully operational. So, hope everyone enjoyed this video. If you did, I'd appreciate a thumbs up, but if you didn't, you know what to do. Huge thanks to my supporters. Names are going off the side of the screen. They make it possible to do this full time. This is my full-time job now. If it wasn't for them, I wouldn't be able to do that. I'd have to get a regular job again, and that sucks. So thanks very much to them, and you can become a supporter. There's links in the description below. Gordon, thanks again for sending this in, and I guess that is going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.